In this video, we're going to talk a little bit more about the differences between exponential growth and decay. So in the last video, we determined what made the difference between an exponential growth model and an exponential decay model. We said that if we have our exponential equation y equals a times b to the x, and a is greater than 0 and b is greater than 1, then we have exponential growth. And if that is the situation, then we call b the growth factor, because it's going to determine, its value determines how quickly our model is growing. We also said in the last video that if a was greater than 0, but b was between 0 and 1, then we would have exponential decay, and it probably won't surprise you too much that in this scenario we call b the decay factor, because it tells us how quickly our model is decaying. Now in this slide, I'm going to show you an alternate way to represent your exponential model. So we've already defined any exponential function to be able to be written as y equals a times b to the x power. And a lot of times that will be the most convenient way to think of your exponential model. But sometimes, especially when we are talking about growth and decay over a certain period of time, it's going to be more convenient to think of exponential growth and decay in terms of this second equation. But I would like to show you how these two equations really mean exactly the same thing. They're just written in slightly different terms. So the second equation, is solved for a of t. And this just means the amount of material or money or whatever at time t. So maybe you want to be able to model, for instance, how much money is in a bank account after a certain amount of time has passed. That could potentially be an exponential situation. Then notice that these a's are exactly the same. That hasn't changed from our first form of the equation to the second. It is important to point out that no matter which way you're looking at the exponential equation, a represents your initial amount, how much money or stuff you are starting with. Now the biggest change here is the difference between b and this 1 plus r value. But don't let this throw you off, because b really equals 1 plus r. And you can use that relationship anytime you get confused if you need to remind yourself of what's going on here. When we write b in terms of, or if we write it as 1 plus r instead, what we're actually trying to do is we're trying to talk about the rate of growth or decay, which is what this r value represents. So what we're saying is that for each time period that passes, that's why we've written our independent variable as a t here instead of just x. For each time period that elapses, I am either growing or decaying by this value r. It's going to be growth if r is positive, it will be decay if r is negative. Alright, let's give this example a try. It says you invest $500 in a savings account that pays 3.5% annual interest. How much will be in the account after 5 years? So the first thing we're going to want to do is we're going to want to write the exponential function that models this situation. And because we're talking about a rate here, this is our 3.5% annual interest that we're earning, we're going to use that second form of an exponential equation. So I'm going to use a of t equals a times 1 plus r to the t power. That's what we want to fill in. So we know that the amount of money in our bank account after some time t has elapsed will be equal to this little a. That's our initial value, and we know that we're starting with $500 times 1 plus r. R being our growth rate, and we're growing here, hopefully you know, because we're earning interest. So this is going to be 1 plus 3.5% is 0.035 to the t power. So all you're going to need to be able to do in these situations really is identify what your a value is, your initial value. You plug that in, and then you need to determine whether you're growing or decaying, and that will determine whether you add or subtract your r value. Here, because we have exponential growth, we're earning interest on this bank account, our r value is positive. Now the specific question that we want to answer is how much will be in the account after 5 years. So we're actually trying to find a of 5 because t is going to equal 5 in this case. So all we have to do now is plug 5 in for t. So this is 1.035 to the 5th power. And when you evaluate this, it turns out that you would have $593.84 in your bank account after 5 years.